Hi, I'm Rajalakshmi, working as an assistant professor in the Department of ECE at R.M.K College of Engineering and Technology. In this video, I'm going to deal with the design of Model Train Controller, which is the design example given in our Unit 1. So this Model Train Controller is designed to control the speed of the train coming on the track. The setup is shown in the diagram. This is a one-way communication system where the control box attached to the track will only send messages to the train, but the train cannot send commands back. There is a unit named as console which is present inside the control box. That control box consists of throttle, emergency stop button, inertia setting button, and so on. So what is that throttle? So throttle is a device which controls the flow of fluid or power to an engine. So I can say it is a mechanical device used to regulate the speed of an engine. Only with the fluid flow the speed will be managed. This device throttle is attached with the control box. The electrical power for the train will be received from the two rails of the track, and the control box can send signals to the train over the tracks by modulating the power supply voltage. This mechanism is shown in the diagram. The train will consist of the motor for the motion of the train and the receiver which is responsible for receiving the messages. The message will consist of the header, address of the receiver, command, and ECC, which is error correction code. The requirement form for the model train controllers is shown here. The name given for the design is Model Train Controller. The purpose of this design is to control the speed of 8 numbers of train on a track. So what are the inputs of this design? The throttle, emergency stop button, and inertia that are attached to the control box will be the inputs to the design. As the design is capable of controlling the speed of 8 numbers of train, so the train will be identified using unique train number, which will one of the inputs. The control signals that are transmitted to the train will be the output. The overall function of this design is to set the engine speed based upon the input received, which is nothing but the inertia settings and the response to emergency stop button. Coming to the performance of the design, it should update the train speed at least 10 times per second. The design consumes 10 watt of power. The manufacturing cost is $50. The size and weight is also mentioned. The Digital Command Control Standard was created by the National Model Railroads Association to support interoperable digital controller model trains. The DCC standards are given in two documents. The first one is Standard S9.1. It is the electrical standard which defines how bits are encoded on the rails for transmission. The second standard is S9.2. It is a communication standard that defines the packet that carries the information. The key note is that the data signal should not change the DC value on the rails. The data signal can swing between two voltages around the power supply voltage as shown in the figure. So logic 1 for 58 microseconds and logic 0 should remain for more than or equal to 100 microseconds. The communication standard S9.2 describes how bits are combined into packets and the meaning of some important packets. The baseline packet has three data types. First one is the address data byte, which gives the address of intended receiver of the packet. The second one is the instruction data type, which provides a basic instruction. The last one is the error correction data type, which is used to detect and correct the transmission errors. The instruction data byte carries several pieces of information. Bits 0 to 3 provides a 4-bit speed value. Bit 4 is additional speed bit. Bit by 5 is a bidirectional bit. So logical 1 for forward direction and 0 for the reverse direction. Bits 7 and 8 are set as 0, 1 to indicate that this instruction provides speed and direction. The basic packet format is expressed as PSA. Within bracket we have small s and d plus e, where P is the preamble, which is the sequence of at least 10 1 bits. A is the 8-bit long address of the unit. Small s is the start bit which is always 0. D is the 8-bit data which contains address, data and error correction information. E is the packet end bit which is always 1. To explain the specification of Model Train Controller, we use a language named as UML, which stands for Unified Modeling Language. So, UML is a visual language that is used to capture the design task. So UML is an object-oriented modeling language used to model the outside world that interacts with the system. Coming to the conceptual specification, the figure shows the UML collaboration diagram. The command unit, which is nothing but the console, and the receiver are represented as objects. The console sends a sequence of packets to the train's receiver. The console sends all the messages as 1 to n, and those messages are carried over the track. This is the UML collaboration for train board component. Command has three components: speed, inertia, and e-stop. All are represented as an individual class. Coming to the functions performed by the control unit, it needs to perform three functions. The first one is to read the state of the front panel, which is present in the command unit. The next is to format messages, which is framing the message for the particular train who is currently on the track. The last is to transmit messages, which is nothing but sending the framed messages to the receiver in the track. The UML class for the console unit using these three functions as a class is shown in the left-hand side figure. The train receiver also performs three functions. The first one is to receive the message. The next is to interpret the message. The third function is to control the motor. All these of train is considered as a class and shown in the right hand side of the diagram. Sender, detector and pulser shown with asterisk symbols are physical objects. The knobs describe analog electronics that sends bits along the track. The detector detects analog signals on the track and converts into digital form. The pulser turns digital commands into analog signals required to control the motor speed. So coming to the console class, it uses three different classes. One is the panel class, next one is the formatter class, and the last one is the transmitter class. The console class describes the command unit's front-end panel, which contains analog knobs and hardware to interface the digital parts of the system. The behavior of the format class is to read the panel knobs and to create the bit stream for the required message. The transmitter class interfaces the analog electronics to send the message along the track. Now coming to the train class, which is defined as a class, makes use of other three classes: the receiver, controller and the motor interface. The function of the receiver class is to turn the analog signals on the track into digital form. The controller class interprets the commands and figures out how to control the motor. The motor interface class defines how to generate the analog signals required to control the motor. Now coming to the detailed specification, the figure shows the detailed specification for Model Train Controller System. The panel has three knobs: the train number, speed and inertia. It also has one button for emergency stop. To change the train's current settings, say changing the train number or to reset the other controls to the proper values, the knob is provided with set knobs behavior. The pulser consists of pulse width and direction. The speed of the motor is controlled by using pulse width modulation. The figure shows the panel and motor interface. Classes for the panel and motor interface. The panel class defines the behavior for each of the controls on the panel. The motor interface defines an attribute for speed that can be set by other classes. So this figure shows the transmitter and receiver class diagram. They provide the software interface to the physical devices that send and receive bits along the track. The transmitter class provides behavior for each type of message that is being sent. The receiver class provides behavior for reading the message. This figure shows the formatter class diagram. The formatter holds the current control settings for all the trains and repeatedly reads the panel and determines whether any setting have to be changed and sent out the appropriate messages. The role of the formatter during the panel operation is illustrated by the sequence diagram. The first change is made to the throttle, inertia or emergency stop, and the second change is made to the train number. The panel is read periodically by the formatter to determine if any control setting is changed. If the control setting is changed for the current train, the formatter decides to send a command. If the train number is changed, the formatter must cause the knob setting to be reset to the proper values for the new train. The train's controller class is shown in the figure. The operate behavior is called by the receiver when it gets a new command. The operate behavior looks at the contents of the message and uses the issue command behavior to change the speed, direction, and inertia setting as necessary. So that's all about the model train controller. Thank you.